All right, hello and welcome again. This is our lecture series on crystalline silicon solar cells. I'm Edward LeBeau. It's actually our last lecture. I hope you've enjoyed yourself and learned some good things to take with you. But let's go ahead and dive in. Today we'll finish up our lecture series on cost. And here's our outline. So first things first, we'll discuss some cost analysis techniques. We'll look into the trends in the market. We'll do some cost projections where the cost is going. We'll do a cost breakdown on the module level and on the cell level. And then we'll do some cost versus technology. So there's lots of different solar technology types and what does each one cost. So there's several different ways to do some cost predictions. There's some different detailed models and things like that. We'll be doing a bottom-up analysis, and that basically takes all the components, just defines how critical they are, what they cost, and then adds them all up, and that's your cost analysis with some other things here and there. But this is highly dependent on some assumptions and present technologies, and this is a fairly accurate and very common cost prediction method. So first things first, we'll look at the solar system installed cost. So what does that mean? That's everything. That's all inclusive. So the solar module is on your roof producing energy. This is the price you're paying for watt. All inclusive. And if you look at it on a residential level, it's about $3.50 a watt. But then on the utility level, so where we're building solar power plants, it's about $1.50 a watt, which is getting pretty close to that dollar a watt we're looking for. Now, this is all without government subsidies, so the government will often subsidize solar energy in different ways. That could be somewhere from $1 to $1.50 a watt in subsidies, especially on the residential level. So solar is becoming quite a bit more competitive in time, and if you look at it, the graph is a steady downward trend. So it appears to be only a matter of time before solar energy will be a pretty similar cost to all of our standard ways of producing energy to now. But here's solar energy on a module level. So if you look at it again, a great drop in cost, a slight spike in 05 to 08. That was some silicon expense increases just from the feedstock. But if you look at it now, it's less than $1 a watt. And doing some quick math, you'll realize that the module is only about a third of what you're paying for. And if you think about it, the module is the bulk of what is going on. But outside the module, there's a lot of surrounding architecture. There's inverters and different power conversion and things like that. There's legal work. There's the steel, the metal that the solar cells have to sit on and mount, and the labor of installation. So that brings up the price, obviously. But here's a breakdown of the module cost. So if you look at this, each color represents a different part of building a solar module and what it costs. The large expense is the silicon feedstock. But if you look at it in 2012, it's about $1.29 a watt. In 2020, it's projected to be about 89 cents a watt on the module level. But there's some advanced concepts that are developing, and hopefully by 2020 it'll be 52 cents a watt. And that'll largely come from increased efficiency, reduced wafer cost, and improved manufacturing and module building. And that'll drop the cost hopefully down to about 52 cents a watt, but these are some advanced concepts and we'll see where they go. And looking at this is called a sensitivity map. So as you go higher on the y-axis, your cost is much more sensitive to change by that variable. So if I wiggle my yield a little bit, go down or up a little bit, I'll have a large effect on my total cost. Whereas if I change my metal paste cost a little bit, that won't have nearly as much of an effect on your total cost. Now then the x-axis is the maximum cost savings available. So if I'm far to the left, there isn't that big of a cost savings available. But if I go further to the right, I have a great cost savings in dollars available. So efficiency is a big player in this game. Efficiency and yield are the biggest players. Now there's all those other things, and of course those are important as well, but our big players are yield and efficiency. Now again, you might give up certain things to change your efficiency. So this isn't just a mad dash of get 100% yield, efficiency as high as possible, well, you might give some other things up that'll really incur some extra costs by doing that. But for the most part, we want to increase our yield and our efficiency to reduce our cost. So here we're going to talk about a simple solar cell, a 15 to 17% cell on the cell level. This is really the most basic way of making a photovoltaic cell. This is just a standard single crystalline solar cell. So here's the cost breakdown on the cell level. So the x-axis is all the different steps in the process and what they cost. The y-axis is the cost. So if you look at it, our big cost incurs are silver paste, materials, and depreciation. And that makes sense. Those are all quite expensive. But let's compare that to this 20 to 22% efficient cell. So this one is a little more sophisticated. Obviously has quite a few more steps to it. There's local N++ areas that'll reduce your series resistance. There's a backside mirror that passivates the back of the cell and is deposited using PECVD. This requires a laser opening to open areas for your screen printing on the back and your front contacts on the front. So again, added complication. And then the front contacts are light-induced copper plating. So again, a more sophisticated process that's obviously more complicated than just screen printing your front contacts. But this results in a 20 to 22% efficient cell. So our efficiency went up, but so did our steps. Let's see what happens to our price. Well, this all adds up to about 23 cents per watt on the wafer level, which compared to 26 cents is not bad, right? So things got a little more complicated, a little more sophisticated, but our cost went down, which is slightly confusing, right? We increased steps and cost went down. Well, the big reason there is we no longer use silver paste in this process. Silver is very expensive. So that is the cause for the reduction, among a few other little things here and there. But again, what's our major costs? Materials and depreciation. So now let's look at this. This is a Group 2 silicon solar cell. This is actually called an IBC, which is an interdigitated back contact solar cell. So there's no front contacts, which increases the efficiency, but adds some complications to your processing. So the back side has these N and P wells going on, which means you need a more sophisticated diffusion process and things like that. So we've increased the complication of building yet again, but we've increased our efficiency to 25%. So here's our cost breakdown. Now this adds up to 30 cents a watt on the cell level, which compared to 23, not so good, right? Our efficiency went up, but our cost increased more than is worth it, right? It's more expensive now per watt. But again, our big two are materials and depreciation. Those are our big two greatest costs. Now this is a Group 3 crystalline silicon solar cell. This is actually called a HIT cell. There's different layers of amorphous silicon that are deposited on it. And amorphous silicon is basically, it's not single crystalline, it's not polycrystalline, it's somewhere in the middle, so there's some amount of a regular crystalline structure, but not quite single crystalline. And then in addition to adding that amorphous silicon layer, there's a thing called a TCO on the front, a transparent conductive oxide. That transparent conductive oxide is indium tin oxide. And that reduces your series resistance and reduces the shading because you need less fingers. Again, this increases the amount of steps and our costs. But let's see what the breakdown is like. Well, again, materials, depreciation, but all the more materials on this, right, from that indium tin oxide. And that adds up to about 31 cents a watt. So again, that went up a little bit more on the wafer level. Now, thinking about it, there isn't a huge difference in the price per watt on the wafer level from each technology, right? We varied from 23 to 31, not massive. 8 cents doesn't seem like a big deal. But when you go on the big module level of hundreds of modules in a power plant, it adds up. It adds up quite a bit. But again, there's other players in the game when you go to large scale. So maybe not necessarily the cheapest on the wafer level will be your best for a big grand scale of power generation. So let's actually look into that. So here's our crystalline silicon PV manufacturing costs for a 500 megawatt per year production of energy. And if you look at it, where our most efficient or our most cheapest cell was the 20 to 22% efficient cell, is actually winning here, right? It's a 51 cent per watt, not on the cell level anymore, but on the module level, 51 cents per watt, and that's for 500 megawatts. Now, let's look at this. This is for 200 megawatts, and if you look at it, no longer is our technology group 1 cell our best option. Now it's our IBC cell, our interdigitated back contact cell, is actually the cheapest for it. And if you look at this, it's largely because of the materials cost is only 9 cents, whereas with technology group 1, it's either 11 or 21. So the thing to note here is not all technologies scale the same. Some scale better at different amounts of energy required, and to really look that up as well, if you're ever in a situation where you're making decisions on what type of cell to use for your house or anything like that, pay attention to how much energy you're looking for and how that technology scales to that energy. So that's all I have for you today. That's actually all I have for you for this lecture series. I'd like to thank you for participating in this, and I'd also like to thank the Solar Power Lab, and Michael and Stuart and Bill for all their help, and also Quantum Energy and Sustainable Solar Technologies and all those involved in that. I hope you guys have a great year, and I hope you've learned something to take with you.